In this video, it will be demonstrated how stone vases can be made using methods that were available in ancient Egypt. After that, anyone will be able to produce a highly precise stone vessel, literally at home, without a lathe or any high-precision equipment at all. Moreover, the time required for production will also be quite realistic. Along with this, several specific technical aspects will be highlighted, all of them feasible, though some require additional effort. My goal was to explain how stone vessels could have been made using simple methods, because that is the first thing that should be verified. Only if such methods proved impossible should we consider more unconventional explanations. When searching for an answer, it's important to keep in mind that the task of producing stone vessels in ancient Egypt was not an isolated one. It was part of the broader question of stoneworking methods in the ancient world. This includes quarrying, traces of sawing and drilling, the making of statues, their detailing and polishing, the carving of hieroglyphs, and finally, the production of vessels. What is remarkable, as noted in the first part, is that virtually every artifact, every work of art, is not perfect in its execution. There are small imperfections in hard-to-reach places or larger flaws elsewhere. The same applies to sawing traces which, as mentioned in a separate video, show irregular direction and non-periodicity. But vessels stand out from this entire body of stonework by their precision. Yet this precision does not refer to the vessel as a whole. It applies specifically to its geometry, and more precisely to the circular accuracy of its horizontal sections. Based on several publications, we can assume that the manufacturing precision of ancient Egyptian stone vessels was about 1/100th of a millimeter, that is, 10 micrometers or even less. In fact, as will be shown later, this is not particularly important. I will also not touch upon the issues of measurement accuracy or methods of subsequent data analysis. These topics are thoroughly covered in videos by other researchers. Here, I will focus purely on the practical side. But before that, it is important to note that we are not talking about accuracy of manufacture, which relates to standards or drawings, but about precision, which refers to how close measurements of the same item are to each other. The term accuracy applies when a part must fit within a certain tolerance range, that is, when it must be made to an exact dimension. This requirement applies to virtually everything, from chair legs to high-precision bearings and bushings. The issue here lies in the acceptable tolerance range that the finished part must satisfy. For example, a bearing, both its inner and outer diameters, must fit precisely into a mechanical assembly. Its tolerances are expressed in micrometers, with several precision classes that vary by type, typically ranging from 1 to 10 micrometers. Precision implies serial production of objects within a defined range of dimensions. In the case of stone vessels, this term can only be applied to a set of points belonging to a single horizontal section, that is, to their degree of circularity. The terms precision and accuracy are not suitable for works of art, where, unless we are dealing with copying, the dimensions are chosen freely by the author. It is unlikely that either a client or the sculptor would demand a statue to be made to a specific height with micron-level accuracy. Nevertheless, an artifact, whether a statue or a vessel, can possess a certain geometric accuracy of form, which is not about matching a technical drawing but about how close its geometry is to an ideal shape. In the case of a vessel, this refers to how close its outer walls are to a perfect circle in a horizontal cross-section. I don't think it would be reasonable to assume that an ancient craftsman aimed to produce a vessel with a maximum diameter of 5 inches accurate to within a few micrometers. The difference between accuracy and degree of circularity is obvious. The former requires measuring instruments to verify the product and adjust the equipment accordingly. In the latter case, measurements are unnecessary. The goal is aesthetic expression rather than technical precision. If there were series of vessels that had identical dimensions and shapes with high precision, the task of explaining the methods of their creation would be somewhat more complicated. And yet, as will be shown later, even that would still be possible. However, all the vessels differ, both in size and in form, which is quite typical for works of art. Therefore, explaining their production does not involve the issue of controlling technical accuracy. The goal was only to create an object that appears as circular as possible. It also does not imply that the contours or the diameter of the neck had to conform to any standards. There were no design, blueprints, or canons of correspondence. It is clear that when people speak of the incredible accuracy of the ancient vessels, They are conflating two different notions. It is not the accuracy of manufacturing that should be discussed, but the accuracy of the methods that allowed the craftsman to produce a shape with minimal deviation from a circular profile of an arbitrary diameter. Whereas, for comparison, the bore tolerance on modern automotive engines is about 10 micrometers, and that refers to a regular passenger car, not to a sports or high-performance engine, where tolerances can be even smaller. This is precisely what accuracy means, the requirement to stay within a specified dimensional limit. Therefore, statements claiming that the vessels have precision, unattainable on modern equipment, are not sufficiently justified. First, such precision is attainable today, and second, these are different notions. A free-form circle is not the same as a structural component made to a specified tolerance. Nevertheless, how could these vessels have been produced? It is obvious that the only natural way for a circle to appear is through rotation, that is, by using a lathe. The most important part of a lathe is its spindle, the axis whose rotation requires a bearing of some kind, including a sliding bearing in the form of a bushing. So, where and from what could such a mechanism have been made in ancient Egypt? And how could it have been constructed so that the runout was minimal or even non-existent? Some authors suggest that it could have been a simple wooden shaft combined with a polished copper or even stone bushing. Indeed, such a design can provide rotation without noticeable play, especially with thick lubrication. But this immediately raises a number of questions. How to deal with the fact that even hard wood wears down, leading over time to looseness and loss of accuracy? And how could a stone blank be fixed onto the shaft firmly enough so that it would not shift or slip during work? A vertical arrangement of the blank instead of a horizontal one could eliminate the influence of gravity, but it would not fully solve the problem of secure fixation. Moreover, when making both the inner and outer surfaces, it would be undesirable to change the fixation, since that could cause the centers of the inner and outer parts to misalign. The optimal solution would be one in which the blank, once mounted, could be worked both from the inside and outside without reattachment. These questions remain unanswered. For example, during the reconstruction experiment by Scientists Against Myths, modern equipment was used, a rotating disc, analogous to a potter's wheel. Obviously, such an experiment made little sense since all the work could indeed be performed on that device. There is no real difference between marking the blank and then processing it, or processing it directly while it rotates. In fact, this experiment effectively acknowledged the existence of a lathe in ancient Egypt. Yet, this should not be seen as a problem. It remains unclear why the academic community is reluctant to shift the appearance of the potter's wheel to an earlier period, one that would correspond to the emergence of stone vessels, especially given that some pottery of that era also shows remarkably high craftsmanship. However, while in the case of clay the adhesion of the material to the surface of the potter's wheel is sufficient for further shaping, with stone, the situation is different. Stone must be worked with force, which means that the blank would inevitably shift, making it impossible to maintain precision. To answer this question, we need to look at what potter's wheels in ancient Egypt actually looked like. Perhaps the answer lies in their very design. This device had a remarkably simple, yet ingenious construction. A bearing in the usual sense was not present. Instead, a cone-shaped recess in stone served as the seat, within which a matching cone-shaped stone element rotated, simultaneously functioning as both shaft and table. It is easy to see that this design eliminates any possibility of runout. As the surfaces wear, the cone simply settles deeper into the socket, maintaining constant contact pressure. Once it reaches the bottom, the flat surfaces further prevent rapid wear. Thus, the problem of achieving a high-precision rotating joint is solved in a very simple way. But another question remains: how to secure the blank to this rotating table? We have come back to where we started. Today, adhesives are commonly used for this purpose. In ancient times, various natural glues made from available materials were also used. For example, animal hide glue produced from skins, bones, tendons, and ligaments. But could such a method be applicable in this case? Was the adhesive strength of ancient composition sufficient to hold a stone blank? This question remains open, as does the possibility that cement-like materials known at the time might have been used for fixation. We, however, will try to find another solution, one that is simple to implement and meets the requirement of reliability. Let us once again look at the shape of the rotating unit, particularly its mating part. If we remove the upper platform and keep only the cone, while remembering that this is a potter's wheel, it is impossible not to recall certain vessels with conical bottoms. In this way, both the problem of fixing the blank and that of the lathe itself are resolved. The vessel itself acts as the spindle, so no additional fixation is needed. Such a design is extremely simple and at the same time very reliable. Moreover, the conical recess could be used repeatedly, each time slightly enlarging its size, giving the lower part of the next blank a matching shape, and then aligning it through rotation. Furthermore, when making a vessel, it was not even necessary for the lower part, serving as the spindle, to fit the recess perfectly. It was enough to grind it at several contact points. Those few spots would be sufficient to ensure stable fixation. This in turn helps explain another question, the nature of the stone slabs with multiple holes in Saqqara, found near the pyramid of Djoser, the very pharaoh who was known for his fascination with collecting stone vessels. These were not specially drilled holes made on a drilling machine, nor were they lifting sockets for wooden levers, as once suggested by Flinders' Petrie. This could very well be a workbench where stone vessels were actually produced. Considering that the table itself is made of a soft material, it was likely used for softer types of stone. Thus, we now have an answer to how a rotating unit could be constructed and how the blank could be secured. What remains is to understand the sequence of operations, how the shaping was carried out, and how the rotation was achieved. The first step was to give the blank its overall shape. After that, grinding was used to achieve the final form and required surface quality. It should be noted that many ancient stone vessels are pitted. Their surfaces contain numerous small cavities. This is easily explained. The craftsman first shaped the rough surface to an acceptable form, but to save effort did not polish it deeply. The presence of such cavities is very difficult to explain if the vessels were made using high-precision, mechanized equipment, since in that case the surface would be completely removed layer by layer, leaving no natural pits. Such cavities could only appear intentionally, not as a byproduct of machining. Therefore, the pitted texture of the vessels demonstrates that there was a rough shaping stage in their manufacture. Indeed, such rough blanks have been found and are displayed in museums. To perform the grinding, rotation was required, but this posed no particular difficulty. It was enough to drill the neck first, then insert a handle or shaft into the hole to hold the vessel while working. After shaping the exterior, the interior could be expanded and refined. It is also important to consider the amount of labor required to produce a single vessel. Obviously, grinding, especially with corundum abrasives, could take only a few days, as could drilling the inner cavity, which is dozens of times faster than reproducing the same results using a rotating table merely for marking. In simple terms, making a stone vessel by this method was a routine task, not something extraordinary. And most importantly, it did not require any special artistic skills. It is easy to imagine a group of 100 workers engaged in vessel production. Such work required no advanced spatial thinking or sculptural ability. It was within reach of almost anyone. The appearance of the rotating mechanism itself could have occurred naturally. While attempting to work on the inner surface of a vessel, the lower part of the blank could have become fixed in a supporting stone through rotation, which may have led to the creation of a potter's wheel of this specific design. In other words, the potter's wheel could have emerged after stone vessels began to be made, not before them, since the stone vessel itself is essentially a prototype of the potter's wheel. It is also worth noting that as early as the Naqada II period, around 3450 BC, there is evidence of socket-type joints being used in architecture. This could have served as a source of technical knowledge for both drilling and fixing blanks during stoneworking. This also provides an answer regarding the curved holes in vessel handles. Their irregular shapes are often interpreted as later modifications, assuming that the handles were not originally intended to have holes. However, the fact that these holes are so varied and often not centered perfectly corresponds to the overall craftsmanship style of ancient Egyptian art. If the accuracy of vessel forms could be ensured by the very principle of rotation, then drilling identical holes in handles would have been nearly impossible with the available tools. Therefore, irregular, uneven holes are actually a sign of authenticity. whereas perfectly round, symmetric holes should raise suspicion, especially if the vessels differ in style, stone type, lack of pitting, sharp handle shapes, and other features. But can such a device really ensure such incredible precision? This question is meaningless. It would actually have been difficult to make a vessel imprecise. With sufficient rotational speed, the surface would be worked until the pits either disappeared or the craftsman considered the result satisfactory. And it is precisely at that point that the observed precision would naturally appear. Another question concerns the manufacture of the inner part, for example, the fact that no traces of copper have been found. It would actually be strange if they had been found, because the optimal method of stoneworking at that time was using stone itself. Why would copper be needed for that? This applies to both the inner and outer surfaces. Therefore, there should be no copper traces on the vessels. The only possible exception might be the initial drilling of the inner cavity, but considering that the cavity was later expanded, any copper particles would have been completely removed in the process. As for the titanium particles reportedly found in some cases, their presence is explained by natural geological factors and is perfectly normal within certain rocks. It is important to distinguish between shavings as foreign objects on an artifact and natural inclusions within the stone. These are different phenomena requiring different explanations. Thus, both the interior and exterior could have been shaped using stone tools of the required form or even emery-based abrasives. With the latter, the labor costs for that era would have been minimal. It should also be noted that the walls of the vessels are not of uniform thickness. They vary from the base upward. If the walls were perfectly uniform, this would imply the use of special equipment for controlling wall thickness, requiring much more complex technical solutions. But in reality, the walls always have variable thickness, which perfectly fits the proposed manufacturing method. Another point is the concentricity of the inner and outer surfaces, the uniformity of wall thickness in a horizontal section. This alignment must have been achieved during the initial drilling of the neck. The simplest way to ensure that is through marking. It should also be noted that the necks of these vessels are not elegant or finely detailed, suggesting that they were first drilled with a smaller diameter, then gradually widened to the desired size. In doing so, the issue of alignment would have resolved naturally through rotation, requiring no special effort. Moreover, not all vessels demonstrate constant wall thickness even at the same level. Of course, during production, the grinding element had to be firmly fixed, otherwise concentricity would be lost. But this is not difficult to achieve. One could use a simple support or employ a sufficiently heavy grinding stone. Additionally, during the process, a template could be created that ensured both shape and precision, making possible the serial production of vessels with similar dimensions. Naturally, such a template could not be used as a grinding tool itself, only for marking. Such a template was needed for working the area between the handles. Once one side was completed, the size could be transferred to the other. Probably this was not always done, which explains why the handles sometimes differ. Apart from drilling the handles, the most obvious challenge in manufacturing was the vertical pattern on the outer surface. It could not be made by rotation, unlike a radial ornament. Therefore, it must have been created manually, inevitably introducing inaccuracies. Unfortunately, there is currently no available data on detailed measurements of vessels of this type. Another important detail concerns cutting off the conical part of the base. There were several possible approaches, for instance, to make a shallow groove by grinding, then break off the excess material and polish the fracture surface. The main issue was not the cutting itself, but ensuring that the bottom remained perpendicular to the vessel's axis so that it could stand evenly. In cases where the bottom was left conical, no additional finishing was required. The only necessary step was smoothing the transition zone between the inner part of the blank still inside the stone and the already finished outer surface. From this perspective, the greatest research value lies not in the most precise or perfect vessels, but rather in the imperfect ones. These unfinished examples can reveal the actual stages of production, the influence of stone type, tool wear, and the evolution of techniques. Both unfinished vessels and incomplete walls tell a story of how the stone was worked and what tools or means were used. Yet at present, most attention is focused on the finished vessels, which, ironically, contain far less information. As a result, nearly all structural features of these mysterious vessels find a reasonable explanation, from their precision to the traces of their manufacture, including the significantly reduced labor costs, which in turn clarifies their large number, as noted in the first part of this study. Of course, the proposed method still requires experimental verification. However, it is not necessary to reproduce the entire vessel. To confirm the sufficient precision of the method, it is enough to make the outer part, and not even at full height. It could be done even more simply by measuring the ancient potter's wheels themselves. They might already demonstrate an adequate level of precision, though, naturally, some degree of wear should be expected. It is worth noting that experiments on reproducing such potter's wheels have already been carried out, so their reconstruction is entirely feasible. Assigning a non-human or extraterrestrial origin to the stone vessels should only be considered if experiments prove that reproduction by the proposed method is impossible. Only then would it make sense to look for other explanations. Thank you for watching and subscribing. See you next time.